Without further ado, let me introduce the next speaker, the first speaker of this afternoon, Lucas Reis. The title of his work is Iterating Negative Polynomials over Finite Fields. Lucas, please.
Okay, thank you. Thank you all for coming. And I'll also like to thank the organizers for the opportunity to give this talk. So this talk is about iterations of polynomials over finite fields. And basically, I'll just give some background on what has been done so far. And well, this talk in particular, I'm mostly interested in one quantity related to the iteration of polynomials, namely the degree of the splitting field of the iterations. Okay, so it's not working.
No more slide. You need to be strong.
No, I think it's not working.
Okay. Yeah, fortunately, I only have like 9 slides, so I have plenty of time. Okay, so let's just fix here. F is a non-constant polynomial over Fq. Fq is a power of a prime p. And then for each positive integer n, I consider the n-fold composition of f with itself. It's denoted by fnx. And the main issue here is to explore the factorization of this polynomial. Right, so for each n, I consider the factorization of the iterate into reducible polynomials. So you will have something like this, right? So we have some polynomials that are irreducible over Fq, and here we might have some multiplicities, right? So and then the main issue here is to obtain the factorization statistics for F, right? And by statistics, I mean like many quantities related, like what is the largest degree of the F INs? What is the largest multiplicity? What is Kn, right? The number of distinct irreducible factors, and so on. Okay, so there's been many works in the past 20, 30 years on the iterates of polynomials over not necessarily finite fields, but general fields. But most of the authors were interested in the so-called stable polynomials. These are the polynomials for which all the iterates, when I take this factorization, right, we have only one factor with multiplicity 1, right? So all the iterates are irreducible, right? So for instance, here there is a work of Odoni in 1997 who consider additive polynomials over function fields, right? So the coefficients is a polynomial in the variable x, and the coefficients are in a field of rational functions over another indeterminate. Also, we have stable binomials over global fields, right? So we consider binomials with coefficients either in a function field or a finite extension of the rationals. There's also a work of Boston and Jones who explore stable quadratic polynomials over finite fields, and actually they explore something more general, which is not stable, they call settled. This just means that the number, at some point, the factors, most of the factors will become stable, right? So the iterates tends to have like a small number of irreducible factors, all with a very high degree. Okay, and more recently in a joint work with Daniel and Arthur, we studied stable binomials over finite fields. Okay, and last but not least, there are 2 works, one from Gomes Pérez Ostafi and Szyparliński in 2014, and another one in 2019 by myself. We explored all these quantities I mentioned, right? So if you look at the iterator, you can consider n as a as a parameter, and so we actually get arithmetic functions, right? So as n goes to infinity, we can ask whether these functions have a defined growth or behavior, right? And so in these two works, we have some partial results towards these questions. And well, as a corollary, we actually, none of these two works actually work properly on the degree of splitting field of iterates, but we can actually get this following this theory. So excluding two types of polynomials, we have there ax to s and ax to a power of the characteristic plus b. So if my polynomial is not of any of these two forms, then if I consider the nth iterate of this polynomial, and I look at the degree of the splitting field, right? So the smallest extension of Fq where this polynomial splits completely, then this degree of the splitting field grows at least linearly with respect to n, right? So in other words, the limit if of this sequence is positive. Okay, and actually this is the best we can get. These two polynomials are exceptions. This function will be constant, so this limit is 0. Okay. But it turns out that many years later, about 15, 20 years later, O'Donnell proved that they're actually this bounded sharp, right? So we have infinitely many polynomials for each the lim sup is also a constant, right? And actually, when I started studying these, considering additive polynomials, I was able to prove his result, but I just found the paper after, right? So basically, the paper was overlooked. It has like, I think, only 4 or 5 citations, but it's a very nice paper. And he actually proves the following. So if I take an additive polynomial, not of the form ax to the b to the h, this plus b here is a typo, then there exists a constant, a positive constant, depending on the polynomial, such that if I consider this sequence, this quotient, the set of limit points of this sequence equals this interval, right? So you can basically think of, if I have here n, and then the function san, if I zoom out the graph, right, this will look like this. So it will oscillate between a constant and b times this constant. And in particular, what we can get as a consequence is that the iterates of additive polynomials are not only reducible, but they will have like lots of irreducible factors, all of small degree, because yeah, the largest degree in particular will grow linearly with respect to length. Okay, so just one some comments on the proof of O'Donnell. He basically transferred the problem to what we call a skew polynomial ring, right? So if we consider the set of additive polynomials, we can easily verify that this is a ring with respect to sum and composition, right? So it's not a product, but composition. But in particular, this ring is not commutative, and this is the problem in a paper, because when we make this correspondence between calculating splitting fields and looking at this skew polynomial ring, this function SAN becomes like evaluation of some ideals, but are ideals in a non-commutative ring. So it's yeah, it took me like 3 weeks just to understand one crucial lemma in the paper. It's very the proofs are very early, actually. But at the end, he provides one example where it's possible to even obtain like an explicit formula for the degree of the splitting field. So if I take A of x as x to the p minus x, and my base field is the Fp, right? So it's a prime field, then I have this nice formula for the degree of the splitting field. And in fact, looking at the rest of the paper, it really looks like he was trying to prove that this holds for every additive polynomial. So we will have a formula like a constant times p to the ceiling function of log p n times something. Okay, and so basically when I found out about the paper, we actually had a completely different proof. The proof I give is actually extremely elementary. We just use basic properties of compositions of additive polynomials. And in fact, we can get something slightly stronger, and we can extend to the class of affine polynomials, right? So the result here reads as follows. I fix here A, an additive polynomial with the same properties in the theorem, and then I fix B, an element of Fq, and I consider B of x as this A of x plus B. So first we have the result of Adoni, right? So this function, the set of limit points go is an interval CA B times CA. But in particular, if I shift this polynomial by a constant, I can also prove that the set of limit points I cannot determine, but I can ensure that is in this interval. So CA P squared times CA. The third property is interesting because it relates the iterations of functions with the constant, right? So as you see, this works as a logarithm, right? So if I take the kth composition of A with itself, the constant associated to this polynomial is k times the constant associated to A. And in fact, well, I cannot give the details, they're a bit technical, but very mild conditions on the polynomial A, we can actually ensure that there is a nice formula for the degree of the splitting field. So we get this equality if n is large enough, right? So we can prove these results. And just here one example. So if I take alpha in F4, satisfying this equation, and I take A of x, this polynomial of degree 8, then, well, we can verify that this polynomial satisfies these mild conditions, so we can actually get a formula for the splitting field, right? And so I also brought a graph of the, yeah, of course, because this is a discrete function, right? So it's an integer, but, well, if you consider the continuation of this function to the real numbers, we get this graph. So it's more or less what I was saying. Of course, we have to zoom out a lot more to see this behavior. But as you see here, here is the number 3 and here's the number 6, right? So the constant here for this polynomial is 3. So the set of limit points would oscillate, the sequence will oscillate between 3 and 6. Okay, so in the paper, we can also derive some results. There are actually more applications of the main results. We don't have to do a lot of work. The first one is basically saying that now if I don't look at the splitting field, but I take look at the degree of each f here, and I take the average, this also grows linearly, right? So this, if I denote sigma A of n, the average for each n, this quotient always lies between two positive real numbers. And in fact, as a corollary, we can actually have a view of the big picture. So if I factorize fnx, if f is additive, most of the reducible factors will have degree about cn for some c. And also we can get one from dynamics. So if I take A, the additive polynomial, I can look at at the induced map, Z goes to AZ over the algebraic closure of FQ. And so for each n here, positive integer n, I can consider the proportion of points in FQ to the n are periodic with respect to A, right? And actually this has been explored for many classes of polynomials and rational functions, and in general the limit doesn't exist, and this is also true for additive polynomials. So in general, this the proportion of periodic points will oscillate between 0 and a positive constant, so we don't have a limit. Yeah, I won't give any proof in this talk, but the paper just got available online, so for those who are interested, you can check there. And finally, I'll just present two problems that arise from this setting. So just recall that we proved that for a generic polynomial, the splitting field, the degree of the splitting field grows at least linearly with respect to n. And in fact, we have this equality, right, if A is an affine polynomial. So the first problem seeks to see whether we have something between linear growth and exponential growth, right? Because, well, it's not hard to see if f is stable and the degree of f is d, then the degree of the splitting field is d to the n. So we have exponential growth, right? And for additive polynomials, we know that the growth is linear, right? So my guess is that there is nothing in between. So if a polynomial doesn't present linear growth, it must present exponential growth. So we cannot have anything in between. And actually, well, is a related problem, determine all the polynomials presenting a linear growth. And again, my guess, this is not a conjecture, it's just my guess. I don't even have enough theoretical support for this, but I think the converse holds, right? So the polynomial must be affine if it has this very nice behavior on the splitting field. Okay, that's all. Thank you.
So how did you get this guess? Because I would not have guessed it, and I would guess it otherwise. So.
Yeah, well, I think it's mostly because of the structure, right? Because for an additive polynomial, if you get a root, you get all the other ones for free, right?
Okay.
Yeah, because they are structure and they will be of the same degree, right? Because, well, if you're like,
yes, but
get this. Like, suppose you're factorizing this guy, right? So, yeah, and you can write in this way, not this way, sorry, in this way, right? So you have if you factorize these polynomials, right? So delta is a root of A, right? And so, but the deltas there are, right? You can obtain the structure of the deltas because you will be a vector space, right? The roots of an additive polynomial form a vector space. So I think this explains why, because like if the polynomial has a root here, you can guarantee that it already splits. This is a very particular property for additive. Yeah, of course. I mean, we don't know if there are other classes of polynomials satisfying this, but yeah.
That's kind of the
yeah. Because I think like if you compose an additive with a monomial, it's gone already. I think it will be exponential. I think this is not even hard to prove, right? So we also have like Chebyshev polynomials, binomials. They will all present the exponential growth, right? So
yeah, I don't know if you know, but it's not the expected degree of the expected splitting field for a polynomial random. Without a polynomial random,
it's exponential.
Yeah. So that's what I'm thinking. This is a very, very special case. So
Yeah. I think I would expect this, right? Because this is also because we're looking at roots, and I think we should always look at the polynomials presenting strange behavior, right?
Yeah.
For instance, for permutations, there are many classes, right, of exceptional polynomials, but they come from Chebyshev, linearized, etc., right? So I think it's a
Did you consider projective polynomials?
sorry.
Projective polynomials.
Projective will be you
They are
take an
related-
additive and divide by.
No, they are
No.
related to additive polynomials.
Sorry.
They are cousins of additive polynomials, actually.
Projective. What? Give me one example.
You divide by x, and then there's a composition of x to the q minus 1 to remove that.
Oh, okay. So you have something like this, AI. Yeah, here's P. Yeah. Something like this. Ah, okay. Yeah. Okay. Yeah. Yeah. I don't know. Because I think here we won't have much structure, right? On the roots. Maybe choosing the TIs, right? If they have like because I think if these guys where AI is not zero, right? If they have like a factor in common, these numbers, and then you can already see this as a composition, right?
So the roots are related, so you basically compose with x to q minus 1. And then
Oh yeah, if you compose with x to the p minus, okay, I know.
And then
I know you're
becomes an
saying
integral.
okay. If you get this is additive.
Yeah.
Okay. Yeah, but I don't know. I think because of this, x to the p minus 1, this might give a because like taking yeah, I don't know. I haven't thought. But yeah, I've seen this. I think this appears as something similar to this appear in exceptional polynomials. You have power of x times f composed with another number.
Well, I think we don't have any questions, so that's time for the couple of pages. The title of her talk is Estimating the number of rational solutions of Markov-Fluid's equations over finite.
Thank you. Good afternoon, everyone. I'm going to start by thanking the organizing committee for the opportunity to speak today. And I also want to say this is joint work with Miriam Abdon, Daniela Oliveira, who is over there, and Mariana Perez and Marina Frecardelli. So let me see if I can move just to the next slide. Yeah, that worked. So this is actually the equation that we studied. Okay, so we call it a generalized Markov-Hurwitz type equation. And we estimate the number of solutions of this equation of Fq, finite field Fq. So these coefficients, the Ai's, A and B, here are elements of some finite field Fq. And then we use this estimate to establish conditions for existence of solutions with non-zero coordinates. So I'll start by saying something about the Markov-Hurwitz equation. So this is basically the equation considered by Markov, and this was studied mainly due to its connection to Diophantine approximations, and then later Hurwitz considered this more general form of this equation. And actually, as far as we know, Hurwitz was the first one to consider this type of equation, which is similar to those, but over finite fields. So here, in this case, the AI's are also in a finite field, and A. And, oh, this was not the next, so sorry. This is the next. So these are more recent works that, well, I consider 2005 kind of recent, definitely more recent than the previous ones. They consider this type of equations as well, so some generalization of Markov-Hurwitz equations. And all of these works are over finite fields as well, so the coefficients are in a finite field. And in some of the works, they were also looking for the number of solutions over Fq of these equations, and they get the formulas for the number. Well, some of the equations, well, the equations are there. We're not, there's nothing cut out of the page, actually. In some cases, under some conditions, they get a formula for this number. In other cases, that's not possible. And actually, the equation we consider comes from this work by Cryptography and Perez, our collaborators in this work. And our equation is just a generalization of this, but also the technique that we use is the same as they are using in this paper. So we're going to follow the steps of the work in the more general equation. Just to give you an idea of, sorry, yeah, this is nice. Just to give you an idea of the sort of estimate that we are going to get, we are going to use this estimate by Cafuri, Materi, and Brigitelli, where they, well, here we consider that V is an absolutely irreducible hypersurface, and we denote this way the number of rational solutions over Fq of rational points in this hypersurface in Fq. And then they have this estimate for this number, where D here is the degree. And, well, in this case, to use this estimate, we need V to have singular locus of codimension at least 2. This is actually the bound that we use in our work. So we're going to try to prove this stuff that we need to use is that we actually are working with an absolutely irreducible hypersurface, and then we try to get a bound on the dimension of the singular locus as well. Okay. There are other bounds in their work that we also try to consider, but then we were not able to use all of them because we actually don't get to prove the necessary steps. So here, I'm gonna say that f is this polynomial, which is given by the equation we are considering, and then v is the affine hypersurface defined by f. This denotes the set of singular points of v, and then this is going to denote the projected closure of v, which is the hypersurface defined by this polynomial, which is the homogenization of f. So we want to prove that this projected hypersurface is absolutely reducible, and then get a bound on the dimension of the singular locus of this hypersurface. So the first thing that we actually get is a bound on the dimension of this set. And for this, we need n to be at least 3, m at least 2, k at least 2 as well. These are just the coefficients of the equation that are non-zero. And then we need the characteristic of the field not to divide mk. These are the exponents that appear in our equation, m and k. And also mk to be greater than n. All this is just so we are able to control the dimension. And the way that we prove, so we have this bound. The dimension of this set is at most n minus 3. And to get this, we actually study the equations given by the partial derivatives of f. So that's why we need this condition, so we are able to say something about this dimension. Well, the other bounds are actually consequences of this one. I have the impression that I skipped something in the middle. Sorry, let me come back here. No, it's actually I'm missing a slide. Suppose. It was supposed to be in the beginning. I'm sorry, I don't know what happened. But we also consider also this other hypersurface. These are the points at infinity. So this is the intersection of the projected closure and the hyperplane with x0 is 0. And this is actually a non-singular hypersurface. And then from the previous bound in this, we have a bound for the singular locus, the dimension of the singular locus of the projected closure, which is also then bounded by n minus 3. So as a consequence of those bounds, we actually can prove that these hypersurfaces are absolutely reducible, and then we can apply the bound to these varieties. Here. So here's the bound for the projected closure. So this now we know is an absolutely reducible hypersurface of degree mk, and this is the bound for the dimension. So we can apply the bound, and then we just get this. For V infinity, we also can use some known estimate, which applies for non-singular ideal theoretic complete intersections. And then we have this bound, and then putting the two of them together, we can bound. This again, I'm very sorry, I'm very clumsy with this. Here, that's the theorem, the first one that I'm going to show you. So then we have the bound. Here n is then the number of FQ rational solutions of this equation. And well, these are actually all the conditions that we had when we got the bound for the dimension of the singular losses. So we carry these conditions here, they come from that estimate. Okay? Well then, after this, we studied the number of solutions with non-zero coordinates. Here I apologize, the statement of the theorem is not precisely correct because we say the number of non-zero solutions. It's not the number of non-zero solutions, it's actually the number of solutions with non-zero coordinates that we are talking here. For this, we just use the bound that we had previously, and then we try to estimate the opposite, right? The solutions with zero coordinates. To count that, we need this extra condition. So here there's the condition that the GCD of n and q minus 1 is 1. So again, this is the exponent that appears for each of the variables in the equation. Oh, well, it's different. Okay, so then we have this bound. And then we use this to give this condition for the existence of solutions. So in this case, I'm showing you the bound for n at least 5, or at least 5 variables here. And then if q is greater than this number, we can guarantee the existence of solutions with non-zero coordinates. Well, and similar, we can get similar results for the other two cases that we considered, n equals 3 and 4, because then it's just a matter of using the same bounds that we had here. But in any case, this is the case for n at least 5. Okay, so some future directions. Well, this is a more general form of the same equations where the exponents here are not the same anymore. And here we have other exponents for the variables on this side. And actually, it's not true that this would be a future direction. Actually, this is a past direction because we started with this equation, but we were not able to bound the dimension of the singular locus for this one. So we still would like to try and do the same thing for this equation. But of course, the idea would be for us to try to apply this technique of studying the geometric aspects of these varieties to give bounds on the number of rational solutions for other types of equations as well. And maybe explore other bounds, because as I said, we used one bound that was fit for this equation and what we were able to prove about varieties, but maybe other bounds known in the literature or some others that we can come up with would also be useful in this kind of stuff. And well, that's all that I have. I would like to acknowledge the organizers of the workshop Diversity in Finite Fields and Coding Theory, which was held in Rio de Janeiro at INPA last year, which is where this work was done. So we are grateful to the organizers of that event. And thank you all for your attention.
Nice. So a couple of questions. So one is about the theorem. You only have the case that sometimes called Taine case, when the characteristic does not divide the degree. Anything possible when the characteristic divides the degree?
Yeah, we actually need that when we look at the derivatives to give the estimate for the bound, which is
Because of the singular, right? When you're studying the singular
the
set.
singular points,
Yeah.
exactly. So yeah, that's probably something we can do when it does divide.
Yeah.
It's going to be a different.
It will be different,
Yeah, it
but
could
I
be
don't know.
different. But
in general,
in general, we could study that as well. It's probably just a little bit harder to do
probably.
that estimate.
Yeah, normally you have the tame and the wild cases, so it probably will be a little bit harder. The second question is about the bounds. For example, this one or any other bound that you have. Did you try experimentally to compare for very small values of the number of variables, like only have 3?
The actual number of solutions?
Yes. So running in some, so there's a computer.
No, we haven't done that yet.
Because my
Of course,
experience is that those bounds are really bad. Very
I think
far
they're
values.
bad. I think they're, yeah, that's
I mean,
that's what I think too,
Yeah.
but we haven't done that yet.
Let me say this again. The bounds is what best we can do mathematically, but as bounds, they are not good.
Yeah, I understand. Yeah, I think they are way off, but we don't know because we haven't done the calculations. No.
It's always, every time I see, and I wonder myself, can someone please try in some small value?
And actually, and then later we got this. These are huge as well. So no, we didn't look at any actual computations for this.
Okay.
Any questions? Comments? Comments, thank you. It's applied to also the speaker signature agent. The title of the program is NDSO equals over F2B. So please.
Good afternoon. First, I'd like to thank you, the organizer of this event, for accepting my presentation. This presentation is a joint work with Isabella and Deborah is my students. Deborah already finished and Isabella are working in this problem yet. And with the discussions with Karina and Sarah. The aim of this presentation is to design a decoding algorithm capable to correct up to 3 burst errors in MDS array codes over F2B. And also I will present a simplified version of this algorithm when we consider a specific case of superregular matrix that is a non-remote matrix. First, I will give some definitions. The first one is the definition of the linear block code. Here, we will use the capital N and K and D to specify the linear code. So this is the parameter that I use. So N is the code length, K the dimension, and then the minimal handling distance. And then we know that a linear block code is capable to detect d-1 errors and correct it up to 4 d-1 by 2 errors. We are interested to codes that archive the equality of the singleton bound. That is when the minimal distance is equal to n minus k plus 1. In this case, we call index codes. And more specifically, we will consider when we will take the code words in blocks. So here we can consider a positive integer b, fixed this b, that divides k and n, capital K and n. And so we construct a linear array codes over q to the b with parameters lowercase n, k, and d, where k and n is related to b, and the minimal distance is calculating considering now this code over fq to the b. These codes are represented by the pair checking matrix 8. And in this case, so we consider the code word with length lowercase n. The result is valid for codes over FQ because here in our example you consider F2, just F2. So I will explain the difference of the errors that we consider. When we consider linear codes, we consider simple vector error vectors like this. So we consider just one bit. And we consider linear array codes. We consider, in this case, we can the burst error that we take our error in a block of the size NB, of the size B, the burst of length B. And here we consider this burst affecting the entire symbol, so we cannot have the burst of the error take a part in a symbol and another part in another symbol. The burst is in all symbol of length B. And now we are interested in linear array code that is capable of correcting burst errors in constructive MDS codes. For this construction, you use some kind of matrix and the mathematical tools. The first of all, you use a super regular matrix that is defined in this way. If is some ever submatrix of A is not singular, which has not all its determinants are non-zero. And you can consider also super regular B block matrix when we consider the full blocks matrix of size B times B is no singular. So you consider this definition. Some examples of super-regular matrix is the van der Waals matrix or Cauchy matrix, some cases for Topliss matrix. And usually it's difficult to find the super-regular matrix. It's hard work. So we use it to use this kind of families. And as you see, when you use the van der Waals matrix, it's very easier. Another matrix that we use in this construction is the companion Frobenius matrix that we constructed by this way. We take a primitive polynomials and we put the coefficients in the last column of this way. For example, in this example, we have these primitive polynomials and the associated Frobenius matrix is given by this way. And the last mathematical clause that we use is the Zach logarithm that is defined by this way. And this logarithm is very interesting in finite fields because usually it's easier to work with power of primitive elements than with addition. In this case, is easier. And we have also this other property that we use at the algorithm. We based this construction in these two papers. So in this paper, they starting with the construction of the MDS array codes, and in this paper of Sarah, they put they started this algorithm for a particular case of two burst errors, and in this work we generalize the algorithm for two errors and also for three burst errors. So the construction is to consider an isomorphism. We started with isomorphism that relates primitive elements with the matrix C, the companion matrix. So we associate a power of a primitive element to a power of a companion matrix. So if we consider a matrix that is composed by primitive elements, we can extend this isomorphism considering another matrix that the entries is the powers of the companion matrix. And by using this isomorphism, we have this theorem that if you take this matrix A as a super regular matrix, so we have an MDS linear array code with parity shape matrix given by this way on in each entry is a power of a companion matrix. So I will show you now the decoding algorithm. The decoding is have many numerical extensive numerical formulas. So I will summarize the algorithm. At the Sarah papers, they consider m equal to 4, and we generalize it to m greater or equal than 4. And in here we consider C, the code word, B, the received vector, and E, the error vector. And the algorithm we use, first we calculate the syndrome. The syndrome is calculated as in linear codes, like this way. And here we separate the information symbols with the parent symbols and the calculate of the syndromes. And so you analyze if the syndrome is equal to 0, if this symbol is different to 0, so the euro is in the parent symbol, in the information symbol, in the parent symbol, and we check all the possibilities that we appear. And the difficult part of this algorithm is when we can relate this vector by using this relation here. We have to associate two consecutive vectors, y, and relate them with a power of the companion matrix given by this expression by using the Zec logarithm. And so this is a worse, the more difficult part of this algorithm. And it happens when we have two burst arrows and the information symbols. But we prove that this algorithm works for all these cases. So we have one or two burst arrows in parent symbols, one in a information symbol, one information in parity, and the case 4, that is the more difficult part to prove, but you have proved that all it works. An example of this, we first see with a superregular matrix, like a Cauchy matrix. So we take a Cauchy matrix constructed by this primitive polynomial and the associated companion matrix of this polynomial. We consider, and in this case, the pair check matrix is given by this way. And we suppose that this is a received vector. For this received vector, we start to compute the syndromes. Just here, in this case, you have just one syndrome equal to 0. So in this case, it is more than one error occur. So we compute the vectors y, and all is different to 0. So combining this two information, we have to false in the case 4. That two errors occurs in the information symbols. So you have to calculate this part that relates the consecutive vector y. But in this case, it didn't work. It means that the second error is not in position 2. So you try in position 3. And here in position 3, it works. The calculation works. And it means that the errors occur in position 1 and 3. So we solve the linear system to find the magnitudes of the errors, and we correct the code. Here, it is the more difficult part. And we prove that when we use the Vandermonde matrix, all of this is equal to the second position of the errors. So it is simplified to make this algorithm. So you prove this recently. And here I will show an example of by using Vandermonde matrix. So if you take this from primitive polynomial, so we have this companion matrix and this Vandermonde matrix. The part check matrix is given by this way. We suppose this received vector. And here I put the calculation just to show But if you see all the results, all equal to, that is the same position of the I be considering, and here words that all these equalities. So the arrows are in positions 1 and 2, and here is the correct value. Next, we will go to the 3 burst arrows. The case to be analyzed that is different is when the 3 burst arrows occur in the information symbols. In this case, we have to relate 3 consecutive indices. And here is much more, many calculations, many complex calculations. But we got an expression to this potential. But it's highly complex if we consider an arbitrary superregular matrix. But I will show here a simplified expression when we use a van der Waals matrix for 3 arrows. It's not so easy, so 2 arrows, but it's better. It's better than if you consider any superregular matrix that we have 2 pages of calculations. The example is similar to the 2 arrows, so I put other example. And now we are working to try to prove that MDS linear array codes can archive the same capacity of the linear codes. We're trying to perform the computational simulation of this algorithm in Python. And you're trying to find other simplifications or alternative algorithms considering different families of the superregular matrix that I'm working with Sarah now. So, thank you.
Do we have any questions? Comments? Suggestions? Well, thanks so much for being here. Now it's time for a coffee break, and we come back at 4:55. Our next speaker is Sandy John. His word is instructions of human beings.
Good evening, everybody hear me? In this talk, I'm going to present a joint work with everybody, Giuseppe Marino and Jojo, about editing code. Specifically, I will show some reconstruction of long QMDS codes, and I will explain what long and QMDS means. Now, this is the overview of the code. We will start with a long introduction to edit code. Then that will be the main part. We will see the construction. And lastly, we will see some properties of the dual of additive codes. Additive code is an FQ subspace C of FQ3H to the N. R will be the dimension of a FQ of C. D will be the minimum weight of C, that is coincides with the minimum distance of the code using the classical M distance. And so C will be an N R over H DQH additive code. And this value, R over H, is the normalized dimension of C, since it lives in FQ3H to the N. And this value can be both an integer or a fraction, and we will be more interested in the fractional case. We can apply the singleton bound to additive codes, and so we will have that the size of the code, which is 2R, is at most the size of the alphabet, which is 2H to the N minus D plus 1. We can do some computation, and obtain that R over H is at most N minus D plus 1. Now, N minus D plus 1 is an integer. We can apply the ceiling, and we can obtain this generalized singleton bound to additive codes. An additive code that reads this bound is said to be quasi-MDS or QMDS. From now on, K will indicate the ceiling of R over H. Now, if we want to compare the classical linear MDS codes with this one, we can notice that we lost a little bit of size, since the classical linear MDS code reached the singleton bound, and these ones reach a lighter version. But what we gain is the possibility to look for codes that are longer than the known MDS codes. I'm missing a slide, I think, but okay. An additive QMDS code is said to be long if its length is more than Q to the H plus 1, which is the length of the solid code. Now we will see an equivalence between additive codes and a set of subspaces. And then we will use this equivalence to construct the new code. So let's see once we have the base of C as an FQ subspace. We can consider a matrix G which has as rows these vectors, and G will be the generator matrix, a generator matrix for C. Okay. We can focus on the column of G, and we can also fix a base B of FQ to the H over FQ. So we can split every element of every column and obtain a matrix in the G, that is a R times NH matrix over FQ, and every column will correspond to a block of H column. We can consider the space generated by this H vectors in FQ to the R, that we will call U1, and U1 will have dimension at most H, obviously. And we can do the same for every block, and we will obtain U1, U2, Un. If the dimension of every Ui is H, we'll say that the code is faithful. And also note that some of these subspaces can be the same. This is possible. So we will consider the multiset T of C containing the dual of such subspaces that we call Wi. This multiset does not depend on the choice of the base B and generator method G, so the name is okay. And this multiset is pretty useful. Indeed, we have that if a code C is equal to U times G, then we have that Cj is 0 if and only if U is in Wj. So it's easy to see that the weight of C depends only in how many of the subspaces of T of C U is contained in. And from this equation, we can also see that the number of subspaces in which U is contained is at most n minus d, since this weight is at least d. So what is T of C? Let's try to understand that. T of C is a multiset of subspaces of F to the R of dimensions at least R minus H, such that each non-zero vector is contained in at most n minus d of such subspaces. This doesn't sound new, and it is indeed a type of R. An NPM backing of F to the R is an n multiset L of subspaces of dimension at least m, such that every non-zero vector is contained in at most t of such subspaces. When n and m are given by the context, we will call it simply T backing. So, what is a T backing is a multiset of subspaces such that they do not intersect too much locally. And from what we said here, we can say that T of C is an n minus d r minus h backing of F to the R. Now, given analytic code, we saw how to construct a backing of this type, but actually, also the converse is true. Indeed, given a backing, we can construct analytic codes. So this is actually an equivalence. So we were looking for long QMDS codes. Now we are looking for n k minus 1 m minus h packing of F to the R. Here there is a k minus 1 since we are in the QMDS setting, so k minus 1 is equal to n minus d. And we are looking this type of packing with n that is at least q to the h plus 2. And in general, we are looking for n to be as big as possible. But how big it can be? Well, this theorem by Bolero and Popazia helps us, saying that if we have QMDS code, then n is at most this value, which depends on q, h, k, and 0, and we call it b, where r0 is the rest between 1 and h from the division of r by h. Now we have all the tools to see the constructions. This is the first one. And this construction tells us that long QMDS codes exist for every choice of Q, H, and K, practically every choice. The only assumption is that K is not too big. How it works, we fix Q, H, and K, and we choose R0 to be at most an integer that is at most H over 2. So we have R to be K minus 1H plus R0, and we choose two subspaces, FP subspaces of Fp to the H as 1 as 2, such that they intersect trivially. The ambient space will be Fp to the H to the K minus 1 times Fp to the R0, and this as a vector space is isomorphic to Fq to the K minus 1 times H plus R0, which is R. So it's the right ambient space Fp to the R. And now given alpha in Fp to the H, we define W alpha to be the subspaces containing the vectors of this type, such that this equation holds, which is an equation of the type x1 plus alpha x2 plus alpha squared x3 and so on, plus alpha to the k minus 2 x k minus 1 plus alpha to the k minus 1 times this combination of elements of the basis and these elements in Fq. So we can consider this sum another element of Fp to the H. Then we will define two other subspaces of the type W infinite i's, and they have the first k minus 2 component, 3, and the k minus 1 is in SI. The last R0, R0. All of these subspaces have the right dimension, which is R minus H. So we consider the set of all of these that has cardinality q to the H plus 2. So the size is right. We need to prove that it is a k minus 1 pi. So We need to prove that given a vector U in the Riemann space, it cannot be contained in K of such subspaces. We divide the proof by cases. Can V be contained in W alpha 1, W alpha K? This would mean that alpha 1, alpha K are solutions of this polynomial in alpha, with just degree K minus 1, so it's impossible, obviously. Can V be contained in W alpha 1 or alpha 2 and in K minus 1 of the type W alpha? Since V is in W alpha 1 or W alpha 2, then these are 0, so U1, U0 are 0. So this sum is 0. So now the degree of the polynomial is K minus 2. We have K minus 1 solutions, still impossible. Last case, we have V in both of W infinite i's, and we have then in K minus 2 of the type W alpha. Now we have still this sum is 0, but also we have that big K minus 1 is in S1 and in S2. So it's in two subspaces that has trivial intersection, so big K minus 1 is also 0. So the degree of this polynomial goes down to K minus 3. We have K minus 1, K minus 2 different solutions, still impossible. So it is actually a K minus 1 packing. We have the equivalence. We have a batch packing. We will obtain a QMDS code on length Q3H plus 2. Now, we can stretch this idea, yes, no, to obtain a long QMDS code with length Q3H plus 3, simply by adding another subspace of this type. But then we need some more assumption on K and H, and I will not focus too much to show this, because the idea is really similar to the previous one. But as far as I know, this is the longest construction of a QMDS code when K is at least 4. And in the case K equal to 3, we can add a lot more of these subspaces of the type W infinite. And again, I will not go too much into details, but as I said, we can add a lot more of this type, and we will obtain a K minus 1 packing of that is at least of this size, and so we'll obtain a QMDS code of length at least this value, which is a length of the type Q3H plus G of 3. Then we will see the last construction. Again, this is the longest construction for K equal to 3, excluding the case Q equal to 2. Now we'll see the last construction, but to see it, we need to recall the definition of a partial spread. A partial S spread in Fq to the R is a collection of n-dimensional Fq subspaces of Fq to the R, such that they intersect trivially pairwise. And a partial spread is said to be full if its elements partitions the non-zero vector of Fq to the R, but a full spread exists if and only if L divides R. This is the construction. It's for the case K equal to, and I remember that we are looking for K minus 1 packing. So in this case, we are looking for 1 packing. And I recall the definition of a T packing to highlight the fact that the definition of a 1 packing coincides with the definition of partial spread, since we are asking to have a non-zero vector to be contained in at most 1 subspace. So it's the same of a partial spread. So this means that if I have an zero-dimensional partial spread, then I have a QMDS code. We can take the biggest zero-dimensional partial spread, let's say omega. Then from some classical results on partial spread by Weierstrass, we know that the size of omega is at least this value. So we'll have an associated QMDS code of at least this length. If R0 divided H, then omega will be the desired spread. In this case, we will obtain a code that has parameters that are the same of a code found by Borlabro and Pupazzi in the same paper as I said before, and this code reached the bound on the left. Now we'll see some properties of the dual. Cool. Okay. Let us define it. Given an additive code C, we can define C verb to be the set of vector B in Fq to the H to the N such that the trace of B times U is 0 for every U in C. We will obtain another additive code that we call the dual of C. And in general, given a QMDS code, the dual is not QMDS. But when this happens, we'll say that C is dual in QMDS. And studying the backing associated to a QMDS code, we found a necessary and sufficient condition for it to be dual in QMDS. But I like to say that this result is actually equivalent to a result found by Martinez Peñas and David Ballesteros. And this result states that given an average D faithful QMDS code with minimum distance that is at least 2, then C is dual QMDS if and only if this condition on the packing T of C is holds. These conditions say that if we intersect, let's take L, and we intersect L subspaces of the packing, we will obtain a subspace of codimension L times H. And this holds for every L between 1 and K minus 1. So it is something like general position of such subspaces. And I think it is a nice structure. And we look for study on this type of set of subspaces, but we found nothing. And actually, if someone has studied them, I'd be happy to know. Okay. And now that we have this if and only if, we can go back to the constructions and see if they are dually QMDS or not. And we have that this, this and this, okay, are not dually QMDS, and it is really easy to find two subspaces such that their intersection has the wrong dimension. And this is dually QMDS, not because it has some nice structure, but because we are in the K equal to case. And in this case, this condition becomes trivial, because we are asking that the intersection of one subspace has codimension H, but this is the same for the code to us to be faithful, so it's trivial in this case. Okay. I lied a little bit because I said that this were never studied, but actually in a specific case they were studied. And is in the case R equal to 2H plus 1, so K is 3 and R0 is 1. I will not go too much into details. I don't think I have I don't have time to go into details. But we have this geometrical object called H dimensional arc that can be defined in Fq to the R. And in the case of R equal to 2H plus 1, this dimensional arc are actually these codes. This type of set of subspaces. Okay. So we have that in this case, dimensional arc is equivalent to a dually QMDS code. Now, there is a bound on the sides of a dimensional arc that coincides with the bound on the length of a QMDS code. If a dimensional arc reaches this bound, is called dual hyperoval, and we have a non-existence result on dual hyperoval. Dual hyperoval doesn't exist when Q is odd. And so we'll have some non-existence results on dually QMDS code. And indeed, we have that there is no dually QMDS code that reaches the bound on the length when R0 is 1 and Q is odd. And K is 3, sorry. But using an operation on additive codes similar to shortening, we can extend this result for every dimension K. And so we will have the same non-existence result. We have an example of a dual hyperoval in the case Q equal 2. That is this one. We have, I will not do the proof, obviously, but we have an example of a dual hyperoval with Q equal 2, and so we have a dual QMDS code associated that reach the bound on the length, and is in the case K equal 3. Okay. So I finished this adding paper I started during my talk, and thank you for your attention.
Okay, so, any questions for Zoom?
So I have one simple question, like what is the real motivation behind studying these QMD scores? Because I think they are far behind the singleton norm. Because I think over there.
Okay. No, yeah, they. They have little codes on the singleton bound. So we have codes that are a little smaller on the size, but we obtain codes that can be longer. So it's really a balance. We lost a little bit of size, but we gained a little bit of length.
So what about the distance? Do you get the it's a more distance? Because length is increasing, but port size is not increasing. I think.
No, yeah, we are studying the case where there is an equal sign. So we studied the case of QMDS code. And this means that if you consider the classical delta singleton, in this case it's between 0 and 1. It's 0 point something. Okay, so we are studying something in between of MDS and an almost MDS. Okay, and we lost a little bit of size, but we gained the length. It's balanced. Yeah.
Any other questions?
Could you show us the references again?
Oh yeah.
We wanted to take it.
Yeah.
Thank you.
Well, thank you. Our last talk of the day, we have Edson Carvalho. The title of his work is Topological Quantum Codes derived from Z and distributions.
Thank you. Good welcome, everyone. First of all, thanks for organizing for me for this opportunity. I share your work today. This work has collaboration with Eduardo Dan Silva and the Paulo Silva Soares. And now you draw the tools, mathematical tools I use in this work. For example, labs, tessellation, platforms, for you obtain topological codes and parameters. And define, I talk about the future direction. Now, I introduce the motivation of this work. Topological codes, just as surface codes or anything codes, are a special kind of stabilizer code construction from tessellation on the flat tops. And all operate X and ZX on the vertex in the face of the tessellation. Logic qubits correspond to homological non-trivial sites on the tops. The motivation is the first work about this is the famous code called that source that use the square lens. And here I use hexagonal lens and another lens to construct a new code families. And we obtain different patterns. Bom, que está essa surface codes, eles defined in the square lens and depend the surface topology. In this work, I will focus in the surface codes in 2 dimensions. In higher dimensions surface codes and polar codes, you see in this reference once my works. Well, the key questions here, you ask, can you build surface codes with the kinetic property using hexagonal lens? Can you link this tessellation to classical perfect codes and less codes? Quem these ideas lead to generalizations for new topological codes in platforms? Now I introduce the LETS in URM. LETS is a discrete typical group generated by interlinear combination of any linear independent basis vectors. Described in this form. Lambda is an n-dimensional lattice with space, and you also possible characterized by the matrix. This matrix depends on the base you chose. And now I introduce some geometry parameters associated to lattice. When you choose the lattice base, you obtain the fundamental regime. You also obtain polynomial regime, the set of the points close to the origin, another old lattice point. For example, in bidimensional lattice with space, you obtain this fundamental regime. Now we describe 2 polynomial regimes for the 2 more famous lattice bidimensional, the square lattice and the hexagonal lattice. And now I describe the sublattice. When you take a sublattice lambda prime of a lattice lambda is a additive subgroup of lambda, and you also formed by the base. It's also helps this matrix creation. The index of lattice prime in lambda is given by this way. In the sublattice lambda prime induces a partition of lambda in cosets. It also possible characterized has fundamental regime associated to lattice and the sublattice given this way. This means the fundamental regime of lambda prime can be covered by the L-pops of the fundamental regime of lambda. To the sublast lambda line induce a partition of the last lambda in F%, given by this way. Now I talk about the perfect code and let's go from the Z2 when we can write in this form, where A and B are positive numbers, interpositive, you can obtain a sublet, right, of square left generated by this matrix. And this last quotient defines a class of perfect code if n also satisfies this equation for some positive integer. In this case, the quotient partition, Z and the power 2 into n least square operators are that perfectly select this. For example, if you take n5, you obtain this perfect code. If n right this form, but not right by this expression, the quotient still defines lattice code, but it's not perfect code. The contour of this code can be used to construct topological quantum codes. And for hexagonal X, you also, if n satisfies this equation, we consider the sublet of hexagonal X generated by this matrix. We also obtain the last quotient defining a class of perfect code, and when this n also satisfies this equation for some positive integer. In this case, the partition uses a least square operator square that selects the space. For example, if you take n plus 7, you obtain this perfect code. However, if n write this form but not satisfy this equation, the quotient still defines this code, but it's not a perfect code. Now I will describe the tessellation of flat orbs in the lattice partition. Basic K idea, we use a less lambda in your subless lambda prime of int n induce a Zn tessellation of flat orbs. When now we describe this proposition in this corollary, that you can obtain when the sublets in the last lambda induce a Zn tessellation. Now I give you some example of H2 class constellation. If let n the fan of Zn tessellation flat orbs, this trajectory is obtained as consequence of fundamental regime of sublets. You have n problems conjoint to the fundamental regime of hexagonal X. Then there are two n qubits up to the 8th. And you take the basis of the sublets of int n in the hexagonal X, described this form. You obtain the distance by this projection, the vector. You obtain the distance of d equal to this form. And now I describe the in this talk I made talk about the supercodes is a special kind of topological code. From the previous slide, we see that Zn tessellation when obtained from the lattice partition defines a supercode with these parameters. Here, lambda is a sublet of hexagonal lattice with these ints. The number of physical qubits is given by 2 times n, and the n equal to the age of the tessellation. Local qubits Q equal to is the genus of the circuit, because in flat dots we have genus 1. The distance is held the minimum cycle length in the tessellation. So this method will also reproduce superpose by using square legs when we have every white disorder. The general idea, the same algebra job formula applies to both hexagonal legs and square legs. For high dimension, it's possible to make, but not put here. Now I describe the sorry. Final remarks. This line of the never stage to design of topological protocols on suits with this is a light correct. The labs and installation take this here also stay to high dimension and for example, when you use the perfect codes, this work, two works of this tree, obtain perfect codes, but one for obtain quantum codes, but one from class perfect code, not for example, for let's go. Let's partitionally construct of superpose for one dimension by defining distillation on flat plots by this form. It has then appeared in the literature handbook in flock holes. It uses particular distillation. However, dynamic generate logical qubits. It uses, for example, hexagonal lens. It's a it's very interesting work here. Well, the key difference in this superpose, statistical source in color poles and plot poles, rate in time periodic protocols a gratitude measurement for fault tolerance. Bom, thank you. This line of reserve naturally extends to design of topological or instances with high dimensions. Using parabolic isolation, you can construct tessellation with infinite many possibles for to consider solid poles, color poles, and clock poles. Because in the hyperbolic plan has infinite tessellation. Again, is for example, for construction color pole and clock pole, it's necessary tessellation must be equivalent and satisfy specific combinatorial properties. This structure generalizes the well-known plot pole and enable new fair a fault-tolerant pole for the most quantum members in the large population. In the future directions combine algebra partition and hyperbolic tessellation offer a great framework to new quantum construction poles. I use this reference. Thank you.
Next one. Any questions? Comments? Comments? Thank you.
Oh, great. So we are receiving some information, but Erivelto is still typing, so. So Erivelto is saying something, but he's still typing. He asked us to give some announcement. So tomorrow will be